I am Sunil Deshpande and we are going to discuss some problems connected with electrostatics. So here is one more beautiful problem on writing the potential difference. Let me again help you recollect that if there is a charged sphere with of course radially symmetrical charge distribution, it will behave like a point charge kept at the geometric center, and potential is a scalar quantity. Whenever you are supposed to write down the net potential, you can always add the potentials. Okay, so let us read the problem. There is a small conducting sphere of radius small r which is inside and concentrically another sphere of radius capital R. The charge on them is q and capital Q. Let us take the charge on the smaller sphere to be small q, on the bigger sphere to be capital Q. They are insulated from each other, which means they are not connected to each other. The potential difference between them is to be written. And let me in the very beginning tell you that this is a beautiful problem based on the concept called electrostatic shielding. Let us first solve the problem, look at the answer and then realize what exactly is this electrostatic shielding. Fine? Okay. See, there are two spheres here. Let me draw them. So this is the bigger sphere, the outer one you can say, and this is the one which is concentrically placed inside. The radius of the inner sphere is say small r and that of the outer sphere is capital R. Charge on the inner sphere is a small q, charge on the outer sphere is capital Q. And he is asking you to write down the potential difference of these two because they are not connected to each other. The purpose of telling you that they are insulated from each other and not connected to each other is, after having connected them by means of a conducting wire, there is no meaning in asking you the potential difference. I hope you understand. Because when you connect them by means of a conducting wire, the potentials of both will become equal and the potential difference is going to be 0. Fine? Okay. So, this is a very important problem. Please look at the solution very carefully. Now, when I write the potential of this sphere, please remember that the potential of this sphere is due to the charge present on itself as well as the charge present on this, right? Because potential is a scalar quantity, I will have to use the superposition principle, write down the potential due to all the charges, then add them in order to get the total potential. So first, let me write the potential of the sphere A. Let me call the outer sphere as B. So potential of the sphere A is K small q divided by small r, because this q has behaved like a point charge kept at the geometric center and I am writing the potential on its surface. Therefore, the distance is small r and k q by small r is what I have written. Now, please recollect again, we have understood this in one of the previous problems that I had taken up. While writing the potential of this sphere due to this charge, remember that this sphere is inside that, right? And please recollect that the potential at all the points inside this outer sphere is the same as the potential on its surface. Whether you write the potential on the surface of this smaller sphere or at any other point inside the bigger sphere, the potential is going to be same as that on the surface. And for that, even capital Q will behave like a point charge kept at the geometric center. Fine? So, I will write it as plus K capital Q divided by capital R. Q is imagined to be at the geometric center. I am writing the potential on the surface. So, distance is R. So, K Q by R is what I have written. But remember that itself will be the potential at all the points inside. So, even on this surface also. Got it? Okay. So, now I will write the potential of B. So, potential of B due to this charge. This will behave like a point charge kept at the geometric center. You are writing the potential on the surface of the outer sphere. Distance is capital R. Therefore, it is K small q divided by capital R. And then this capital Q is also at the geometric center. You are writing the potential on its surface. That will be K capital Q by capital R. This was also K capital Q by capital R only, but remember at that time you were not writing the potential on its surface, you were writing the potential on the surface of the smaller sphere, right? But whatever was the potential on the surface of the bigger sphere was the potential everywhere inside, so it was also the potential of the surface of the inner sphere. Got it? Now you want VA minus VB or VB minus VA because he says only potential difference between them. So either write VB minus VA or VA minus VB. What you will get is, if you subtract VA minus VB this k q by capital R gets cancelled. It is only k q by small r minus k q by capital R, which is k q into 1 by small r minus 1 by capital R. See, k q into 1 by small r minus 1 by capital R. Fine? Okay, but the beauty of this problem is you could see here that the potential difference between these two spheres had got nothing to do with the charge on the outer sphere. Capital Q has got no significance. You change that capital Q to 2q, you make it minus 3q and still write the potential difference between these two spheres, that will turn out to be only dependent on the charge on the inner sphere. Fine? Of course, on the geometry of the outer sphere, no doubt, but the charge on the outer sphere has got no significance. This is exactly what is called as electrostatic shielding. That is, you change the charge, you change the field outside, the potential difference between these two is not going to be affected. So, the outer charge and the outer field has got no influence on the potential difference between these two, especially when you have enclosed one sphere inside the other one. So, this sphere has basically shielded this one. So, this is what is electrostatic shielding, and your first option is perfectly correct. So, now we are dealing with dipole and dipole moment. So, let me first brief you about what exactly is this dipole. See, dipole is a charge configuration basically, due to which if you try to write the field somewhere, it turns out to be inversely proportional to cube of the distance, and if you try to write the potential, it turns out to be inversely proportional to square of the distance. That is how I think we can define what is a dipole. But the simplest type of dipole that we have in our syllabus is the one which constitutes only one point negative charge and another point positive charge separated by some finite distance. And especially you can call the dipole to be an ideal dipole provided the field or the potential that you want to write will be at a distance which is much larger as compared to the separation between these two charges. That is, minus q and plus q, they will be held separated by some distance, say a. This a has to be very small in comparison with the distance at which you are writing the field as well as the potential due to a dipole. You can call the dipole to be an ideal one at that time. Fine? Okay, so that is about the dipole. Now, there is a beautiful problem here. There are 3 point charges q, minus 2q and q, and they are placed at some well defined points. So, q is placed at 0 a 0, I think this is on the y axis at a distance of a from the origin, minus 2q is placed exactly at the origin, and q is placed at a 0 0, which is on the x axis at a distance of a from the origin. The magnitude and direction of the dipole moment of the assembly is to be written. So, this is just an idea, I think you have to only enjoy this and you can extend this if required. So, this dipole moment is a vector quantity, and that is one of the charges, preferably positive, multiplied by the separation between the two charges. If you say the distance between the two charges is a, then q into a is going to be the dipole moment, where q is going to be the positive charge associated with your dipole. I said what is a dipole? Constituting of one minus q and another plus q, both are point charges separated by a distance of a. So, q into a gives you the dipole moment, but this is only the magnitude of the dipole moment. Direction has been conventionally decided to be from minus q to plus q. So, direction will be along the line joining minus q and plus q, directed from minus q to plus q, and magnitude will be q into a. So, after having understood this, let us try to write the dipole moment of our assembly. See, you have been given 3 charges. Let me draw them like this. See, this is the origin, this is your x axis, this is y axis. The charge which is kept at the origin is minus 2q. The charge which is kept on the y axis is q at a distance of a, and the charge which is kept on the x axis is also q, also at a distance of a. Now, thinking of this as a system and trying to write its dipole moment, I have to imagine like this. I told you this is just an idea. There is one minus q here and one plus q here, which makes it act like one dipole. Another minus q here along with this plus q will make it act like one more dipole. Fine. And what about the dipole moment magnitude? Q into A. This is also Q into A, right? And the direction of this dipole moment is going to be along the y direction, and the dipole moment of this one is going to be along the x direction. So, the resultant of this QA which is along the y axis and this QA which is along the x axis will lead to under root of QA square plus QA square, which is QA root 2, directed exactly along the angle bisector. And if you imagine this to be a perfect square with side A and A, this will be exactly the diagonal. So, the direction of the resultant dipole moment of your system is from 0, 0, 0 to A, 0. I hope you agree that this point has got its x coordinate also as A, y coordinate also as A, z coordinate 0. So, the resultant dipole moment is under root of QA square plus QA square, which is root 2 QA, directed along the diagonal. So, that makes your C option perfectly correct. So, here is one more problem on dipole and the electric field due to the dipole. So, let us read it. The electric field at a point due to an electric dipole where on an axis at an angle theta, of course less than 90, to the dipole axis is perpendicular to the dipole axis. What is theta? So, what he means here is, this is the dipole, right? You can say this is minus q charge and this is plus q charge, and the dipole moment is from negative charge to positive charge. So, you can say this is the dipole axis, and inclined at an angle theta less than 90 to the dipole axis, he has taken a point. So, say the point is here somewhere, right. So, this angle is theta, this is the point that he is talking about, and the electric field there is perpendicular to the dipole axis. So, here you are going to get two electric fields, one because of the change in the value of R, which is in this direction, you can call it as E radial, and this is another value of E, another component of E, you can say. The resultant electric field at this particular point will have these two components, one because of the variation in the value of R, and second because of the variation in the value of theta. So, you can call this as E theta, and then the resultant of these two will be the electric field under root of E r whole square plus E theta whole square will give you the resultant electric field. So, if you say the resultant electric field is like this, making an angle alpha with E r, then tan alpha equal to half tan theta is the relationship. One student I think will be very comfortably remembering this particular relationship. You can write the electric field there due to this dipole at a distance of r at an angle theta with the dipole moment direction, and that resultant electric field will have these two components, one because of the variation in the value of r and second because of the variation in the value of theta. The resultant of these two is E, which I have shown here in between these two. That makes an angle of alpha with ER. That alpha is given as tan alpha is equal to half tan theta. Now, what he is mentioning here is this resultant electric field is perpendicular to the dipole axis. So, this is the dipole axis. So, perpendicular to the dipole axis means like this. Fine, perpendicular to the dipole axis. So, which means alpha should be 90 minus theta. See, if I draw one line parallel to this axis, right, this angle is theta, so this angle will also be theta, corresponding angles. I hope you agree with this. Now, if this is theta, alpha should be 90 minus theta. Now, the resultant electric field is not like this, it is perpendicular to the axis. So, this is the direction of the resultant electric field. So, if this is the resultant electric field and alpha is the angle that the resultant electric field makes with ER, that alpha should be 90 minus theta. So, instead of tan alpha, I will write tan of 90 minus theta equal to half tan theta. That makes cot theta equal to half tan theta, or 2 equal to tan square theta, 2 equal to tan square theta, and tan theta equal to root 2, theta equal to tan inverse of root 2. So, that makes your C option perfectly correct. I hope you understood this, and I hope I was quite clear in explaining the things. This is the dipole. We are talking about a point which has been chosen very generally at a distance of r from the midpoint of the dipole and at an angle theta with the dipole axis. You can say dipole moment direction. These are the two components of the resultant electric field there. This is the resultant electric field. If it makes an angle alpha, tan alpha is equal to half tan theta is the relationship. But here he says the resultant electric field is not like this, it is perpendicular to the axis. Therefore, that alpha should be 90 minus theta, and that makes your C option perfectly correct. So, one more problem on understanding of the flux associated with the electric field. So, let me read the problem first. A hollow cylinder has a charge q within it. If phi is the flux associated with the curved surface, the flux associated with one of the plane surfaces is how much? See, this is a very beautiful problem because it is based on one principle called as superposition principle. There is no way you can find out the flux associated with the plane surface alone. In fact, because integral of E dot ds to be carried out everywhere on the plane surface is impossible, because it is a point charge which you have kept inside the cylinder, and where have you kept we do not know. How is the electric field on the plane surfaces we do not know. So, calculation of integration of E dot ds over the entire plane surface is simply ruled out. So, it is only with the help of the superposition principle that we can think of solving this problem. Fine. So, what does it say? See, there is a cylinder which has got two plane surfaces and one curved surface, and it is totally enclosing a charge q. Therefore, what should be the flux coming out of the whole cylinder? The flux coming out of the whole cylinder should be 1 by epsilon naught times the charge enclosed by the cylinder. So, that is 1 by epsilon naught times q. This is the flux which comes out of the entire cylinder consisting of two plane surfaces and one curved surface. So, I will write this as flux coming out of the plane surface plus flux coming out of the curved surface, out of which flux coming out of the curved surface you have assured us to be phi, and you are asking us what is the flux coming out of the plane surface. So, that makes the problem very, very simple. So, flux coming out of the plane surface is the total flux minus the flux that comes out of the curved surface, which you have given to be phi. So, this is the answer, provided you had asked me the flux coming out of both the plane surfaces taken together, but out of which you are asking the flux coming out of one of the plane surfaces. Therefore, we can say it is q by epsilon naught minus phi, half of this. I hope you followed this. Right? This is the flux which comes out of both the plane surfaces taken together, and your question is about the flux which comes out of one of the plane surfaces. With an assumption that the flux coming out of both the plane surfaces is equally divided among the two surfaces, we can select B to be the correct option. I hope you understood this. This finding of equivalent capacitance between two specific points, I think, is one of the very common problems that you come across in electrostatics. Let me tell you one thing. In any given circuit, the capacitors need not be always either in series or in parallel. Sometimes you may not find them either in series or in parallel at all. And moreover, do not be of the do not have this practice of looking at a circuit and immediately concluding that these are in series, those are in parallel, and so on and so forth, because unless you are given two specific points across which you are supposed to look at the whole circuit, you cannot decide which of them are in series and which of them are in parallel. Fine. So, that is one thing, and secondly, they need not be always in series or in parallel. Fine. Okay. So, let us read the problem. This is a given network of capacitors. He says all the capacitors are identical, their capacitance is C, and you are supposed to find out the effective capacitance between A and B. So, you can see here that he has clearly given you two specific points, and he wants you to calculate the effective capacitance between those two, or else simply given a circuit, I cannot start judging which of them are in series and which of them are in parallel, right, only because he has mentioned A and B and he wants you to find out the effective capacitance between A and B, we can proceed. So, there is a special method which I am going to adopt in this particular problem, which you can remember and carry forward. What is that? See, if this point is A, I can call this point also as A. The reason is, this point has been directly connected to this point by means of a conducting wire which does not have any other capacitor or resistor or whatever. So, there is no other circuit element and there is just a bare connecting wire. Therefore, this point should be having the same potential as this. So, if you have called this point as A, I must have to call this point also as A. Similarly, if you have called this point as B, this is also B and this is also B for the same reason again. Then if I call this point to be C, this is also C, this is also C. That simplifies the whole network. Now, if you start looking at all the capacitors, like the first one, this has been connected between A and C. This also has been connected between A and C. This is also connected between A and C. And then this is the one which is connected between B and C, also this, also this. So, the 6 capacitors that he has given in the network, out of those, 3 of them have been connected between A and C, and the remaining 3 have been connected between B and C. So, that simplifies the whole network for finding the effective capacitance. So, what I will do is, I will just redraw the network. This is my point A, this is somewhere C, and this is your point B. You are asking me to find out the effective capacitance between A and B. Between A and C there are 3, and because all of them are between A and C only, they should be in parallel, and the effective capacitance of capacitors connected in parallel is C effective equal to C1 plus C2 directly. So, C plus C plus C makes it 3C here, and then there are 3 more connected between B and C, again all of them in parallel. So, that makes it 3C again here also. Now, there are 2 3C capacitors connected in series between A and B, and in series, if 2 capacitors C1 and C2 are connected, C effective is going to be C1 C2 divided by C1 plus C2. So, 3C into 3C divided by 3C plus 3C makes it 3C by 2. So, that makes option D perfectly correct. So, here is another problem on a network of capacitors, slightly one step ahead of what we had done in the previous one. In the previous problem, I think we were only concerned about the equivalent capacitance between 2 given points. So, here there is one step more than that. So, let us read the problem. So, this is a network of capacitors with the respective capacitances very clearly written. A potential difference of 60 volts is applied between A and B what is the potential difference across the 6 microfarad capacitor is what he is asking. So, our approach here would be to find out the effective capacitance between A and B first, then you will be reducing the given network of 5 capacitors to only 1, and then with a given potential difference applied across that capacitor, you can find the charge which flows from A to B. Knowing the charge, knowing the capacitance, you can always write the potential difference using the formula C is equal to Q by V. So, let us first reduce this. See, there are 2 capacitors here which are in parallel and they directly get added up, and that reduces to 6, and then you have 2 6 in series which reduces to 3, and then you have 3 capacitors each of 3 microfarad capacitance all connected in series, and that reduces to 1 microfarad capacitor between A and B. So, there is only one capacitor of 1 microfarad connected between A and B. I hope you understood this. These two are in parallel, so they directly get added up, and that amounts to 6 microfarads. This 6 and this 6 in series reduces to 3, because the formula is C1 C2 divided by C1 plus C2, and then you have 3 capacitors each of 3 microfarads. This combined making one 3, second and third, and when all the 3 of them are in series, they reduce to 1 microfarad. 1 by C equivalent equal to 1 by C1 plus 1 by C2 plus 1 by C3. Okay, so now you have applied a potential difference of 60 volts across 1 microfarad capacitor. Therefore, the charge which will flow from A to B is Q equal to CV. C is 1 microfarad and potential difference that you have applied is 60 volts. So, 60 microcoulombs is the charge which flows, and remember that charge will flow from A to B. So, it starts from A, and the charge which flows through this 6 microfarad capacitor is 60 microcoulombs, and you are interested in the potential difference across this. So, V equals Q by C. Q is 60 microcoulombs, C is 6 microfarads, and 60 by 6 is 10 volts. Therefore, the correct option here is A.